Right, today we are going to talk about, I'll say, sort of the application of what we learned, the Fourier transform. Very important, like some Fourier transform with the sinc functions. Okay, so first, if I have two functions multiply in time, so for sinc functions, then in frequency domain, we do the convolution. Okay, well, even though it is a multiplication, but you see that for the two sinc function, if they times together, that's kind of complicated. But you do the convolution of the pulse function. That will be much easier, right? So here, multiplication in time. We will get the convolution in frequency. Okay, so let's see. First, you need to know for the sinc function, there in Fourier domain, there'll be a rectangular pulse like this. Okay, I have a WT, then here the width will be 2W, from minus W to W. You can either, but we don't, well, you may see this is like a W divided by pi sinc W divided by pi T. Okay. Because we say that the sinc function, here's a note. With a sinc function, that means sine pi t divided by pi t. But now I have sine sine wt divided by pi t. So if you want to write it down, the sinc function is like this. You can derive it. Not that hard. I just did it. So you can do it by yourself. If you can't make or express this fraction into the sinc function, just let me know. Okay, so for the rectangular pulse, it's just either 1 or 0. 1 is when the omega is less than or equal to W. Otherwise, it will be 0. So if I do the convolution times 1 over 2 pi, so there'll be 1 over 2 pi. 1 over 2 pi times, for the first one, W1t, so my width will be 2W1. Here's omega. Right, for this one, here the amplitude is 1. And then from minus W1 to W1, convolve the second one, W2. So my width should be 2W2. So here's 1 and then W2. So from minus W2 to W2. We learned this before, right? When we talk about the convolution. Two rectangulars. If I do the convolution, what do we have? Either trapezoid or a triangle, right? So if W1 and W2 are not equal, then, right, suppose W1 is less than W2. So in this case, we will get a trapezoid. The height is W1 over pi. And here's minus W1 plus W2. This is W1 plus W2. And this point, that is W2 minus W1. You can see that. All right, so I window in here. So convolve. So because W1 or W1 is less than W2, so W2 should be bigger. Anyway, so like in this case here, inside, I have the same value, right? Until that I windowing out, and finally it's 0. When it is 0, that will be W1 plus W2. Okay. So for the spatial case, when W2 equals W1, okay, so there's no like flat region, we will get a triangle, which also means that this is a sinc function square. So the Fourier transform will be, the width will be 4W. Height will be W over pi. Okay, any questions so far? Next, we are going to see that two sinc functions convolved in time. Then in frequency domain, we have two rectangular pulses multiplied together. Okay, and we still assume that normally W2 is always less than W1, but we assume here W1 is less than W2. So we convolved in time domain. So convolution in time domain, we will get multiplication in frequency domain. Right, since W1 is less than W2, so when they times together, what do we have? Rectangular times rectangular pulse. Still rectangular pulse, right? But the width is W1 or W2. So suppose W2 is here, W1. So when they times together, we keep W1. So that means to copy this. So when we write, so you can see, well, so what is the answer here? One single function convolve another single function. What is the result? Still in time domain. Okay, I mean sine W1t divided by pi t convolve sine W2t divided by pi t should be equal to what? Not in frequency domain, okay? I know in frequency domain, I times this together, I get the omega W1, right? This rectangular pulse. So when I do the convolution, actually in frequency domain, I still get the rectangular pulse for W1. So that means when I do the convolution in time domain, here, single function, right, W1. Okay? Because you get this one, right? Rectangular pulse in frequency domain, that means I have a single function in time domain. And since the width is W1, so here. Okay, any questions for this? Here we should also say that W1 is less than W2. Okay, here's the example. Let's consider this input signal. Okay, the signal is a sinc function plus the cosine function. So first we can plot the magnitude of the signal in frequency domain. What is the magnitude? Well, we have two parts. Okay, so at least we need to know the sinc function in frequency domain and also cosine. So for the sinc function, okay, in frequency domain, that's a rectangular pulse. The width is from -2 to 2, and the magnitude here is 1. So this is a signal. I use red. From -2 to 2. So from -2 to 2, and here's 1. And let's see cosine. Cosine 8t. I will get maybe this -8 and 8. Magnitude, the height is pi. That's right here. So cosine 8t. If I do the Fourier transform, I will shift to the right and shift to the left. So pi times delta function. I shift to the right and shift to the left. So if I just, let's see the square later. So I have two signals add together by linearity. Okay, I can add this together. So when I add this together and then do the Fourier transform, that also means in frequency domain, I just add this two. So I should have, this is from -2 to 2, and the height is 1. And also, at -8, I have pi, and 8, I have pi. Okay, so far so good. Now let's see, because we need the square. The square means that I need to time this together. If I want to time this to A times A, in frequency domain, I'm doing the convolution. Okay, so actually I'm doing the convolution. Let's quickly plot this. So from -2 to 2, and then pi, here's pi, and -8, and also pi at 8. And from -2 to 2, I have magnitude 1. So therefore, I need to convolve this. So when you convolve this, let's see. Okay, so you flip, and then you just, well, actually, this is at 0, right? At 0, I will have what? When you do the convolution at 0, I need to find the area. So the area is 4 plus the pi times pi twice. And then first you shift to the right. When you shift to the right, so actually because they are the same rectangular poles, so you get a triangle in the center. All right? And then finally, you will also get 2 pi in some time duration. Here will be 2 pi. And finally, you will get pi square. Right? When x is 16, you get pi square. Also, you move to the left, you also get the pi square at -16. Okay, so here you should have at -16, I have pi square. Here's pi square. Also 16, I have a pi square. And at 0, I have 2 pi square. So this is pi square, 2 pi square, and pi square. And from -4 to 4, I have a triangle because I have two exactly the same rectangular poles to do the convolution. So here I should have here's 4. And when you like move this around here and here, you will also get a rectangular pulse, which is 2 pi. Okay, and then you times 1 over 2 pi. Okay, so finally you just change the magnitude. Okay, here you have pi over 2. Pi over 2. And then pi. And this is 2 over pi. And this is 1. And 1. This is one way that you can find the Fourier transform, or how do we express the signal in frequency domain. The other way, you can just take the square out, okay, really do the square, and then you do the Fourier transform by terms, which means that this square, there will be sinc function square and the cross term, and then cosine square, and you do the Fourier transform, Fourier transform, and Fourier transform. Okay. So, in this case, sinc square, what is the Fourier transform? Since they are the same, right? So the Fourier transform, you do the multiplication in time domain. In frequency domain, I do the convolution. 2 rectangular pulses doing the convolution, you get a triangle, right? So now here we have a triangle. From -4 to 4. The magnitude is 2 over pi. And cosine square. So again, the cosine convolved the cosine in frequency domain. So you can think of this. We are doing convolution. At 0, I have a pi times pi plus pi times pi. So I should have 2 pi squared, right? And I shift. When 16, now I match. I have 2 pi, pi squared. I also shift to -16, I have a pi squared. Okay, and then later on you divide by 2 pi. So you should get here is pi, and then pi over 2. And pi over 2. So this is pi, and at 16, -16, I have pi over 2. And 16, I have a pi over 2. And here is 0. And now let's see the sinc function and cosine function. When they times together in frequency domain, they are doing the convolution. So again, for the convolution, you can either switch this or this one. So if you doing this, for example, at 0, nothing. When they reach to -2, so when they move 2, I got pi, right? And I got pi till here, and 0. Also that if I move to the left, when I move to the left, then I'll get pi from -6 to -10. So you should get 1, 1 from minus 10, minus 8, minus 6, 6, 8, and 10. Now this is just a signal, all right? So finally we have, we can express the signal in frequency domain. Now this signal is going to send to the LTI system. Let's see, what do we have at the output? So now, the signal is going to send to the LTI system. And then for this system, I have an impulse response. Okay, the impulse response is what? What is this? A sinc function. Okay, first let's have our result here. This is our signal. So let's copy this. Right, this is our signal X. Okay, hopefully. All right, so now I send the X to the LTI system, and this LTI system is a sinc function. So since it is sinc function, let's plot the amplitude in frequency domain. So sinc function, my frequency domain will be a rectangular pulse. Okay, so here is the rectangular pulse. The width is from -5 to 5. So from -5 to 5, I have 1. Magnitude is 1. Remember that in frequency domain, we'll do the multiplication. X times H, right? Because in time domain, we are doing convolution. So in frequency domain, we do the multiplication. So now, H multiplied the X. What do we have? From -5 to 5, I have a value. So from -5 to 5, I have a value. Otherwise, it's all 0. So when I time these two functions, I only preserve this part, right? If I reserve this part, let's just plot here, which means I have pi at 0, and also from -4 to 4. From -4 to 4. From -4 to 4, we have the peak is 2 over pi. Then what is the output in time domain? Right, who can tell me the output in time domain? I give you that in frequency domain already. Let's try this. If I give you this, what is the output in time domain? How can we get this triangle pulse? Triangle in frequency domain. That means in time domain, what do we have?
Two sinc function convolution.
Say again?
Two sinc function convolution.
Sinc function, right?
Yeah.
So here I have a sinc function, time sinc function, a convolved sinc function. No, time sinc function. So I have two sinc functions, and they are exactly the same width. So here I should have sine 2t divided by pi t squared. this gives you the triangle pulse, right? And then for pi here, you get 1/2. Because the delta function, the Fourier transform is 1. And then, here's the Fourier transform. You get 1. But if you do the Fourier transform again, you get 2 pi delta function minus omega. So if you want to get pi here, actually you have 1/2. All right. Now suppose I send the signal to another LTI system. The impulse response is a sinc function times cosine. What does that mean, that something times cosine? When you have something times cosine, then that means that you are doing modulation. So you shift to the right and shift to the left by 8. Okay, and sinc function in frequency domain, that is a rectangular pulse. So you can also think this is like 1/2 pi your rectangular pulse from -4 to 4. And the magnitude is 1. Convolve cosine. So I have 2 sterns. So one is 8 and one is -8 at -8. Okay, so in this case, I'll shift this to the right and shift this to the left. So my impulse, the frequency response, will be still rectangular pulse, but I shift. So here is from 4, 8, 12. Magnitude is 1/2, 1/2, -12, -8, -4. All right, so this is my frequency response. What is output response? The output. The output, okay, this times here, -4 to -12, here. And here. So I preserve this yellow, 2 yellow rectangular pulses. Okay. So I have -10, -8, -6. Here 8, 6, and 10. And this is 1/2. 1/2. All right, so tell me what is the output in time domain? Why do we have 2 recurrent pulses here? It looks like something I shift to the right, something I shift to the left, right? So if I shift to the right, shift to the left in time domain, what does that mean? I'm doing the modulation. I should have something times cosine. Right, so I will shift to the right, shift to the left. So in time domain, I should have something times cosine. correct? What is something? That something is a rectangular pulse. How can I get the rectangular pulse in frequency domain? That means in time domain, what do we have? Sinc function. So what is the sinc function here? Check the width. So if we move back to here, it is from -2 to 2, right? So here I should get sine 2t divided by pi t, and then you times cosine at. You don't need to really do the inverse Fourier transform by the formula. Okay? During the break, you can also think about this. If I send it to another LTI system with the impulse response, two sinc functions times together but different width, then what should we get? Remember that if I have a different width, so the result should not be a triangle, right? It should be a trapezoid. Okay. All right. So for two sinc function multiplication in time domain, in frequency domain, I will do the multiplication, convolution. So we'll get a trapezoid. Okay, so here the trapezoid looks like this one. So we have -6, -4, here is 0, 4, and 6. The height is 1 over pi. So from -6 to 6, here from -6 to 6, and let's see the magnitude. It should be here, here to here. So I still preserve everything. Okay, so y3 is just like y1. F1 and also the red one. So it's from -4 to 4. Here's 2 divided by pi squared, and then the blue one is 1. So this means the y3, the output, is here we have different. Here's 2 over pi squared. So I get 1 over pi. To get the triangle in frequency domain, that means in time domain, I have the sinc function times the sinc function. So sinc squared, sine 2t divided by pi t squared plus 1 over 2 pi. Right, next, I send to another LTI system. The impulse response is this one. If you see the response in time domain, what do you expect in frequency domain? Every time when you see cosine, then you will know that in frequency domain I will shift to the right and shift to the left. Okay? And then two sinc function times together in frequency domain, and they are different width. They have a different width. So in frequency domain, I should have a trapezoid. Okay. So these two in time domain, doing the multiplication, in frequency domain, I have 1 over 2 pi. So the first rectangular pulse, that's from -3 to 3. So here, from -3 to 3. And the magnitude is 1. The second one, the width should be -1 to 1. So from -1 to 1. Also magnitude 1. So in this case, when you do the convolution, you should get a trapezoid. From -4, 0, 4, 1 over pi, and then this is 2. Here is 2. Okay. So now this in frequency domain here. Now doing the modulation, I shift to the right with 8 unit, shift to the left with 8 unit. So here, so this middle 0 will be here 8. -8. Correct? So let's do the shift here. Okay, so here it's 1 over pi, 1 over pi, from -12, -4, well, here we have -10. All right, the middle is -8. Here's -10, -6, 4, 6, 10, 12. Right, and here's the x. Here's the x. What is the output? The yellow one, right? Because from 4 to 12 here, -4 to -12. So I preserve this too. Okay, so I preserve that too. This is 1/2, 1/2, 6, 8, 10. -10, -8, -6. Okay, then what is the output in time domain? What is the output? This is the output in frequency domain. Then how about in time domain? You don't need to give me the answer, but the concept. Because I have a rectangular pulse, so in time domain, I should have what? Sinc function. And I shift, right? So I should times cosine. So I have, and what is the sinc function? This width is 6 to 10 is like from -2 to 2. So this is sine 2t divided by pi t times cosine. I shift by 8. Next, I send it to another system. Here is our impulse response. Sinc function and shift. So now I can move it quickly. So sinc function and move. Then I should get this rectangular pulse. This is 1/2, 15, 16, 17. And shift to the -16, -17, -15, 1/2. Right. So in this case, I preserve this two. Okay. So I get at 16, I have pi/4. At -16, this is -16, I have a pi/4. And then pi/4 here for 16. Then what is the output? If I have two sterns in frequency domain, then in time domain, what do we have? Because I have a cosine and I shift to the right, shift to the left. Okay? You can also think about this is (16t). Okay, last one, I hope. Or not yet, actually. All right, so for this for this case, I send it to the system. Again, it is a sinc function and I shift. So I hope that you can catch this concept so we can do it quickly. This should be 4, 5, 6, -6, -5, -4. In this case, what is the output? 5 or 6, I have a value, but 5 or 6 here is 0. Here is 0. Okay, h, this is x. H times x, I only have a values from 4 to 6, right? But here is nothing, nothing. So the output is what? 0. 0, let's use, I don't know, maybe this color. So this O0. Right. Last one, you are sending to the impulse train. So now if you send it to impulse train, what happens? Actually, this is still a sinc function, right? Times the impulse train. So at least we know sinc function times the impulse train. In frequency domain, then we do the convolution. So first we need to know what is the sinc function in frequency domain. It is a rectangular pulse. We have already done this for the past hours. So here, from -4 to 4, and here is 1. What is the impulse train in frequency domain? Okay, so for the impulse train in frequency domain, last week we mentioned that this is like a periodic signal, right? So for the periodic signal, your transformation, well, your Fourier transform, it is still like a Sturm and with a period. Okay, so remember that we can express your signal in this series. And then we can find the coefficient. So this one, I think I can write here. Here's a note. Let me see. For the rectangle, for the pulse train, the Fourier transform is still a pulse train, but they have a different width and the magnitude. Omega minus k 2 pi over t. And then omega naught will be, we'll write this later. Okay. You can also think this is, if we express that in Fourier series, e to the j k omega naught t. 1 over t, the coefficient is 1 over t. So it's 1 over t, k equals minus infinity to infinity, 2 pi delta function, omega minus k omega naught. The omega naught is 2 pi over t, the fundamental frequency. So the Fourier transform of this impulse train will be also like every night I have an impulse. Every night I have an impulse. The magnitude is 9. I have a 9, 0, 9, 18, minus 9, minus 18. The magnitude is 9. And the period, 2 pi over 9. So, in this case, in frequency domain, I'm doing a convolution. So when I do the convolution, I'll get a lot of it will be like a rectangular pulse train. Okay, let me plot this. From minus 4 to 4. So from minus 4 to 4, and then 5 to 13. The middle is 9. The second middle is 18, from 14 to 22. The magnitude is 9 over 2 pi. Here's 0. Minus 5, minus 9, and minus 13. Okay, and then you can see the x, all right, times your frequency response. You will see all the information are preserved, which means, okay, and then this I need to times 9 over 2 pi. So your output is 9 over 2 pi x, so which is 9 over 2 pi sinc function plus cosine. All right, let's see another example. If I have this x1 is 2 pi t times the sinc function square, you can also think about this as one sinc function times 2 sine function. Okay, because 1t will cancel out. So only one sinc function. Again, they are also doing kind of like a modulation here. Okay, so your frequency domain looks 2 times. You shift to the right and also shift to the left, but since you are timing sine, not cosine, so you will have 1 over 2j. Okay, so suppose I have there's a Fourier transform omega naught. We will define omega naught later. The shift 5 to the right and also shift left, shift 5 to the left. And actually, this is omega naught, the magnitude of omega naught. Its sinc function will be a rectangular pulse in frequency domain. So this is a frequency domain with here's -5 to 5. And you see that if I shift to the right 5, they'll be here, right? And shift to the left by 5 here. So overall, actually, what is your x1? If we plot the magnitude, so we don't need to care about this imaginary part. You will get from -10 to 10, magnitude 1. Okay. Now I have another signal, x2. For x2, this is like a sinc function, but for the sinc function, I also shift by pi over 10 to the right, and also pi over 10 to the left. So in this case, I can think of there's a sinc function. Shift to the right, shift to the left. Correct? Okay, so this is x2. What is the Fourier? What is the frequency domain? How do we express the Fourier domain? I do the time shift in time domain, what do we do in frequency domain? At times the exponential, complex. Right. I have the same magnitude but different phase. So here I should still have 1 over 2. The magnitude is the same, so z naught omega. You times 1 over 2. And this is the complex exponential. E to the minus j omega pi over 10 minus e to the j omega pi over 10. And you can times j and divide by j. Here you have 2j here. So what is z naught omega? Sinc function. So for this sinc function, the width is 10. So from minus 10 to 10. Minus 10 to 10. And then at times this is like a sine function. So my x2 looks like McDonald. The magnitude is 1 from minus 10 to 0, 0 to 10. Okay, now I have two signals, x1 and x2. I would like to combine these two signals, but not just doing the not just add them together. Okay, I modulate the first signal and also modulate the second signal. Okay, with a different frequency. Okay, then what is the Fourier transform in frequency domain? First, I do the modulation, shift by 30. So for x1, the x1 is like s1, shift to the left and shift to the right by 30. And how about x2? The x2, I also shift to the left and right by 60. Okay, so how do I plot this x? Well, I think I should get two different color. Well, anyway, shift by 30. This one. So let's have 10, 20, 30, 40, 50, 60, 70. Here, minus 10, minus 20, minus 30, minus 40, minus 50, minus 60, minus 70. Alright, so first, this shift to the right by 30. So 0 to 30 here. So I should have this rectangular pause. Let's have like orange from 20 to 40. And then from minus 20 to minus 40. And then shift to the right by 60. So 0 will be here. So I have a McDonald here. This is McDonald. Okay, so now this is my signal. And now I have this signal, send it to the LTS system. And then the impulse response is this one. Two sinc function times together, and then I do the modulation. So in each table, please draw the answer here to make sure that you know how to draw. Okay, so magnitude here, 1, it is from 10 to 50, minus 10 to minus 50. So in this case, well, compared to here, from 10 to 50, minus 10 to minus 50. So I preserve this 2. If I preserve this 2, what does that mean? This output y1 is 2x1 cosine times 30t. Right. This is here. Next, if the impulse response is this one, sinc function, shift, doing modulation. So shift by 45. So here you should have like a rectangular pause. Magnitude is still 1, 40 to 50, and minus 40 to minus 50. And check here, 40 to 50, minus 40 to 50, minus 50, nothing. So you get 0. Okay. Next, similarly, I have a trapezoid, shift by 60. So here magnitude is 1, 40 to 80, minus 40 to minus 80. So in this case, we only need to know from 40 to 80, minus 40 to minus 80. So I preserve x2, right? So x2, that means 2x2t cosine 60t. Now if I have another signal, this signal is 2 of your original signal x and doing the modulation. Okay, so in this case, what is the Fourier transform? That means this is my x, and I still need to do the modulation. Shift to the right by 30, and shift to the left by 30. So if I shift to the right by 30, I will have rectangular pulse here. And shift to the left, this one will go back to here. So I'll have two rectangular pulses symmetric by the y-axis. So in this case, we will get let's mark the axis 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. Minus 10, minus 20, minus 30, minus 40, minus 50, minus 60, minus 70, minus 80, minus 90, minus 100. And for this two cosines, you can use the formula. Two cosine theta cosine phi will be equal to cosine theta plus phi plus cosine theta minus phi. So you can also think the overall the signal is 2x1t, and then shift by 60. x2t, shift by 30, and shift by 60. Plus 90. Right, so where are we? Now we have another signal. And then the output. So output is obtained from part D. Okay, so what is the output? CT. So this is actually this is the output. And now we are going to have this as an input to another system, which is the low pass filter. This is a low pass filter. So when this is a low pass filter, we can plot this is trapezoid. So for low pass filter, this is minus 20, 20, magnitude 1. And then this is 10. This is minus 10. Minus 10, 10. Okay, so after having this low pass filter from minus 20 to 20, this is 1 here. So I only preserve this. So to preserve this, which means WT is ZT convolve H4, but we will only get this one, which is X1. Okay, this is X1. So using this low pass filter, we get X1. In the beginning, let's see that in the beginning we have two signals. You can see that in time domain is a sinc function square, and also sinc function shift by time. So if you just see the time function in time domain, and it's like this, it's pretty nasty. This including X1 and X2. We want to extract these two signals. What should we do? We can do some tricks to make it into the frequency domain using the modulation. When you use the modulation, you can see that I separate these two signals in different frequencies. And then later on, from different frequencies, I still times kind of like doing the modulation. Okay, that all the frequencies back to the baseband, and then I use the filter to fill out. Now I fill out here, so I got X1. I can fill out this part, then I'll get like a bandpass filter here, then I'll get X2. Okay. And you can see that for our filter, it's better to have either like a rectangular pause or trapezoid, which means that in time domain that is a sinc function. So that's why that in the beginning of this class today that we learned the sinc function and also its Fourier transform. We're doing the multiplication or convolution in one domain. How do we deal with that in another domain? And for those examples, you can see that different impulse response. It is like this is like a filter. Okay, you fill out the signals in frequency domain. Okay, so here we are going to talk about the filtering. We only focus on those three filters: low pass filter, high pass filter, and band pass filter. We have more filters, but when you learn digital signal processing or the advanced processing, that you will learn other filters. But here we just have a really basic introduction of those three filters. What is filters? You can see that we can use the frequency response to select frequencies. So actually filtering means I select the frequency. So I'm selecting frequency. Frequencies. Then I can what? To rebuild the signal. So, for example, if I have frequency response is j omega, okay, let's plot the magnitude. The magnitude is like omega, so it looks like here. You can see for this frequency response, they will amplify the high frequency. So for those high frequencies, they will amplified. But for the low frequencies, they will attenuate till 0. Okay, so this, you can see that for this frequency response, the amplifies high frequency. High frequencies, let's just write a high frequency, and also attenuate the low frequency. So in many applications, we say that we want to modify the spectrum of a signal by either amplify the high frequency or attenuating the some frequency components, just like what we did here. Okay. So filtering means that this kind of processing, the process of modifying the frequency spectrum, is called filtering. And the system doing this filtering operation is called a filter. So today you can see that we send the signals to different systems, and they are doing the filtering. So those systems are called filter. So for the frequency selective filters, they will pass some frequencies with probably just little or even no distortion, so I can preserve that signal. So the basic types of frequency selective filters are like low pass filter, high pass, and also band pass. First, let's see what is low pass filter. So for low pass filter, I just keep okay, we talk about that later. First, let's see what is an ideal low pass filter. For the ideal low pass filter, may eliminate all frequency components with a frequency that magnitude is greater than some cutoff frequency. Okay, such frequency, I have this form. For this omega is less than or equal to the cutoff frequency, I preserve that, it's 1. Otherwise, it is 0. Let's plot this right away. So it looks like omega here, h of omega. This is the cutoff frequency. I only preserve the frequencies in this region. For the low pass filter, I can smooth the signals. So actually, this can keep the slow changes. To smooth the signal. For example, like now you have a lot of apps on your phone, right? They can, it's called blur filter. So for the blur filter, I can remove the high frequency details. Like they can remove the edges, they remove the noise. remove high frequency details such as the edges and noise. Or another example, like the car suspension. They may remove the high frequency vibrations. Like if I have a road bumps, they can remove that vibration. So maybe here. The car suspension, they try to remove high frequency vibration, like road bumps. And the high pass filter, that means I only pass the high frequencies. So it's like opposite of this. So you can see that when omega is greater than or equal to the cutoff frequency, it's 1. Otherwise, it is 0. So if you plot this, okay, this is 1. So, for example, like a sharpened filter. They just try to enhance the edges. The blue filter, we said that this is low pass filter because we want to remove or eliminate the edges. But the other way around, that means for the sharpened filter, I want to enhance it. So enhance edges. So for the high pass filter, I want to keep the rapid change. Like the sharp sound. For the low pass filter and high pass filter, there's a relationship. Here you can see the high pass filter is just the delta function minus the sinc function. This is here, right? Hopefully that for these 3 hours, at least you know that this sinc function, the frequency domain, that's a rectangular pulse from minus cutoff frequency to cutoff frequency. Delta in frequency domain, there'll be like O1. So it'll be O1 here, minus this. Then I got the high pass filter. Then for bandpass filter, from literally that I want to only keep a specific range of the frequency. So I'll keep only a specific range. Like the radio station. You don't want to hear all the stations coming together, right? So using the bandpass filter, I can just watch some specific channel. So I can select one station and then ignore others. So the bandpass filter looks like this one. Here's 1 minus omega c, c2 minus omega c1, omega c1, omega c2. All right. That's all for the Fourier transform. Okay, next topic we are going to talk about the discrete time Fourier transform. Because so far we just learned Fourier series. Fourier series in time, in continuous case and also discrete case, and then we move on to the Fourier transform. Okay, also for the continuous time case. How about discrete time? Here we can talk about it. For the discrete time Fourier transform. Okay. Let's see the definition here first. It's discrete, so we take the discrete time Fourier transform. Again, that is like a combination. Or you can also think about this as a coefficient. So your signal times their basis. The inverse, similarly, the signal is the coefficient times their basis. Okay, and doing a linear combination. And the difference is here. They only integrate for 2 pi. Okay. So let's write it down. The integral over period of 2 pi. Let's just see some examples and then explain it. For example, this is our signal. Okay, let's plot this signal first. This signal looks like decreasing. So we have here decreasing. Okay. So what is the discrete time Fourier transform? Let's take a look. So discrete time Fourier transform, this one you can also think about like a coefficient. How can I get the coefficient? Signal times your basis. So signal times your basis. Your signal is 2 to the minus n, a unit step function, e to the minus j omega n. So I only have, when n is greater than 0, I have a value 1. So this I have 2 to the minus 1 e to the minus j omega over O to the n. This is your ratio. So this is 1 divided by 1 minus e to the minus j omega over 2. Now just pay attention to the result. Let's see the next example. This is x. Can you plot the signal? So how does it look like? Give you the axis and you plot. Okay, suppose it's here. This is 0, 1, 2, 3, minus 1, minus 2, minus 3. Okay, please plot this signal. How does it look like? So I only have values at 0, at minus 1, and also at 1. And the value is 1. Okay, so here we can say that x at minus 1, e to the minus j, oh, hold on. Over or divided by, this is, wow. E to the minus j omega divided by 2. Okay? So this is minus j omega minus 1 and x of 0, e to the minus j omega 0, and x1 e to the minus j omega 1. So you should get e to the j omega plus 1 plus e to the minus j omega. This, I think, for you right now is not obvious. Actually, this is 1 plus 2 cosine omega. Okay, still keep in mind about the result. 1 plus 2 cosine omega. The first one is, well, here we have the complex exponential. Okay. So from these two examples, what do we have? Cosine is periodic. This is also periodic, right? Because e to the j omega j theta will be cosine theta plus I sine j sine theta. It is also periodic. So this is the transform. Okay, the transform is periodic by 2 pi. So the discrete time Fourier transform x is periodic. And the period is 2 pi. I think this should be here. So omega periodic with period 2 pi. Because x omega plus 2 pi, let's see, if I have 2 pi here, which means this summation x, this is e to the minus j omega plus 2 pi n. And for the omega plus 2 pi n, this is x e to the minus j omega n, and also e to the minus j omega, no omega, 2 pi n. So what is this term? E to the minus j 2 pi n. How much? 1. So because this is 1. So overall the summation is xn in the product there are bases. So this is the Fourier transform. That's why it's periodic by 2 pi. Keep in mind the result here. Besides periodic and 2 pi for your Fourier transform, what else? We will talk about it next week.